So something I want to make sure that we kind of really understand is this whole checked, unchecked. Um, so there's two types of categories, unchecked and checked. This is unchecked exceptions are those that inherit from the error class or the runtime exception class. Recall that um, these exceptions that inherit from the error are thrown when a critical error occurs, such as running out of memory. Basically, we can't handle those. All the rest are basically checked exceptions, and those are things that we should be able to handle. Um, it says all of the remaining exceptions, that is, that do not inherit from error or runtime exception are checked exceptions. These are the exceptions that you should handle in your program. It must handle the exception, or it must have a throws clause in the method header. The throws clause informs the compiler of the exception that could get thrown. So file not found exception is one of those that we have to deal with. If we don't basically handle it within our code, we do have to have it in our method heading. So with that being said, like I said last time, if we have a throws and we don't have a catch, it's going to display a bunch of red text at the bottom. Now, one thing that we can do is, I'm on page 725, and it says we can write code that throws one of the standard Java exceptions or an instance of a custom exception that we have created. So what we can do is, let's just go ahead and open up the code. Let's open up die. D-I-E, die. Do you have that one? I don't think you do. I don't think it came with the... So die looks like this. It basically says public die int num size, so it's basically a class, die, and then it's got 3 instance variables. Should say it's got a constant and 2 instance variables. And here's our constructor, int num size comes in, and it basically says if num size is less than min size, we're going to throw a new illegal argument exception. The die must have at least min num size. Then if it has the right number of sides, then it's going to set the instance variable size equal to num size, and then it's going to do a roll, and then it's going to basically do everything. And I think we've seen this before. The only difference between this die and the die we've seen in the past is it's got this throws argument exception. Now, if we open up the dice exception demo, we can see there that we have a final int die size equals 1, so we got a constant for that. We go ahead and instantiate our die object called lowercase d die, and we instantiate it as a new die. We're going to pass in die size, which is 1, so that's going to cause an error. And then we're going to say the initial value of the die, and then we get the die value. And so when we run this, now notice we did not have a catch statement. So like I said before, if we don't have a catch statement, the compiler is going to handle it. And notice it's got the die must have at least 4 sides. So when we basically said throw a new illegal argument exception, and here's our message, it displayed that message, but where did it display it? It displayed it down here. And again, we probably don't want our user having to see this type of thing, because it's going to say that, hey, it died on line 26 in the die class. And they're going to go, I don't know what the die class is, line 26, and here it is. So, and it basically got called on line 9. So basically, here's our stack trace. So, but again, the whole point of this is to let you know that if we don't have a catch statement, this is what's going to happen. Okay, on page 729, here's what we can do. We can actually create our own exception class. And so let's take a look at negative starting balance. And right there, you'll notice that it says public class, negative starting balance, and it extends exception. So we are inheriting everything that's in the exception class, but we're creating our own exception called negative starting balance. And here is our constructor. It's negative starting balance, and it's going to call the super. So it's going to basically call the constructor in the exception class with the message error negative starting balance. Now, that's a no arg constructor. If we actually pass in a double, it's going to basically print error negative starting balance, and it's going to actually have the amount. And again, it's going to call the supers, which is the exception classes. It's going to call that constructor. So how the heck do we use this? Well, we use this just like we would any other exception. I'm going to open up the account test. And there we see public static void main. We got a try, and this is where we have our bank account, new balance, and it's got negative 100. So it says if we get an error trying to do that, the catch statement says it's going to call the negative starting balance, and here's the E object that gets created from the negative starting balance. We got system out println e.get message. I remember that what we put in that throws clause is what gets put into the message. So when we run this part, it comes back and says error negative starting balance. So the whole point of this is we can create our own specific error message exception. Shut the door. So there we've got our own exception class specifically designed for what we need to use it for. In this case, we had a bank account class, and we do not want to have a starting negative balance. And so we basically created an exception class just for that. So any questions on that? Now, one thing that we would like to stress is when we create this exception, are you okay? Okay. When we create this our own custom-made exception class, we would like to always include this parameter so that when we create our Java doc, these @ symbols, so we can have an @ exception. It's talking about there on page 731, using the @ exception tag in the documentation. And it basically says negative starting balance when the starting balance is less than 0. So how does that work? Well, I don't know if I ever got this to run, but let me show you how it works. I'm going to click on project. I'm going to click on generate Java doc. And in there, it's going to look for, you have to have the path to the Java doc in here, and I'd have to go find it again. But I was able to get it to run, and it will actually put it in the same workspace that your code is at. So if I come over here and I look in my workspace, and I go to chapter 11, I now have a doc folder. If I double click on that, I do have an index.html. I double click on that, and look what it creates. This looks identical to what the Java API looks like. And I can actually click on this negative starting balance. And there it says, hey, I'm inheriting from exception, which inherits from throwable, which inherits from object. And it comes up here and says negative starting balance exceptions are thrown by the bank account class when the negative starting balance is passed to the constructor. Where is that at? Where does it display that? Right there. So there is that note right there. So that gets passed into that. And then it's got the negative starting balance constructor. No arg, this constructor uses a generic error message. negative starting balance, when we pass in a double, this constructor specifies the bad starting balance and the error message. And again, where did those come from? Well, if we look over here, this constructor uses a generic error message, and this constructor uses a specified a bad starting balance. And down here, it's got throws, negative starting balance when the balance is less than 0. Remember where that came within that parameter there? So anyways, all those @ symbols that we put in here help us document our code when we basically create a Java doc. And it's automatically created by just running the Java doc application. It's pretty cool. And we can basically then store this somewhere. We'd probably want to grab this entire folder, this doc folder, and actually grab that entire doc folder and then store it somewhere so that we basically can have access to this at any time. So again, if you had to maintain this code, this is probably where you'd want to start to figure out what was going on. You'd basically go to the Java doc folder, open it up, see where all the parameters are, what's being passed in, what's expected of this particular code, so on and so forth. Okay, with that, let's go back to our code that we tried to do last time. So on page 732, we now are going to talk about binary files, random access files, and object serialization. So the very first thing the chapter talks about is this thing called binary files. So let me do this. Let me bring up the textbook real quick. That way you can kind of see what they're talking about. So binary files are just what you think they are. Binary files are all zeros and ones. That's all they are. So how it works is we have all the files you've been working with so far have been text files. So what we've seen so far are nothing but text. That means the data stored in these files have been formatted as text. Even numbers, when stored in a text file through the println method, are converted to text. Okay. So we've seen a print writer output file, new print writer number.txt, and we can basically write to it. So when we write to it, so if we write the number 1297, this is what it looks like inside of a regular text file. So when a number such as 1297 is stored in the computer's memory, it isn't stored in text, however, it's converted to a binary number. And this is what a 1297 looks like in binary format. So the binary representation of a number shown in figure 11-4 is the way the raw data is stored in memory. In fact, it is sometimes called raw binary format. A file that contains binary data is often called a binary file. So the great thing about binary files is there's no conversion that is done. So when the computer reads a binary file, it doesn't have to do any conversion because it's ready to go, because that's what the computer knows is all binary. If it's string, it has to convert it into a binary before it uses it. So that's kind of the great thing about using binary files is there's no conversion to be done. It just basically grabs it, reads it, and it's ready to go. So to write data to a binary file, we must create some objects from the following classes. We need a file output stream and a data output stream. So the file output stream allows you to open the file for writing binary data and establish a connection. Data output stream allows you to write data to a primitive type or string objects to a binary file. So what it looks like is this. I'm going to instantiate a file output stream object, in this case fstream, instantiate it as a new file output stream, and this is where I put in my file name. Then, again, what that does is, like I said up here, it opens the file and establishes a connection. The data output stream, in this case output file instantiated as a new data output stream, it's going to use the file stream. So it basically then goes into that file and gets it so that we can now read data from it. Okay, so this guy opens it and establishes the connection. This guy down here actually gets us ready to read and points us to the first record. Down here, warning, if the file you are opening with a file output stream object already exists, it will be erased and an empty file by the same name will be created. So, what types of methods are we basically going to use with an data output stream? Well, we have close, just like any other file we've used so far. When we open it, we need to close it when we're done. I can write a Boolean. So here's my write Boolean. Notice it's got void. So it returns nothing, but we have to pass it a Boolean and it's going to write it. We can pass a B byte and we can write a byte. We can write a char. We can write a double. We can write a float, an int, a long, a short, and write a UTF. What's a UTF? We'll see that here in a second, but a UTF is basically a string. We don't call it a string, they call it a UTF, which is Unicode text format. So let's take a look at our very first program called the write binary file. So we come in here and open up a write binary file. So let's take a look at this guy. We've got a public static void main, and in there we create an array, an int array called numbers, and we go ahead and put 2, 4, 6, 8, 10, 12, 14. So here's where I create my file output stream object, fstream, and it's going to basically be called numbers.dat. So just opened the file and made the connection. I create my data output stream, output file, and instantiate as a new data output stream. I'm going to use fstream, which then basically gets us ready to read that file and has us pointed at the very first record. We then write, sys out, writing the numbers to the file. We're going to use a for loop. We're going to go through that array one item at a time. So there's our int I equals 0, while I is less than numbers.length. We're going to come in here. We're going to say output, write int, numbers I. So we're going to grab each element of that array and write it to the file. When we get done with that, we're going to write done. And then the very last thing we're going to do is output file.close. Simple enough. It's a very simple program. When we run it, oh, I hate that. It's still pointing to my old program. So let me do a right click on write binary file, and run as Java application. There we go. Writing the numbers to the file, ... done. Okay, not real exciting for us, but here's what I want to do, is I want to open up that file. So I'm going to go to my workspace. You don't have to do this, you just watch. So I go to my workspace, I open up chapter 11, and go to, oh, am I the right one? I'm in lab. Chapter 11. And there is numbers.dat, right? Numbers.dat. I open it. And this is what it looks like. Well, the reason it's writing all these numbers, so these blocks there, is because it tried to open up a binary file. And a binary file has just that, binary code. So it's unreadable to us. We can't read it. So opening this file in whatever editor I have is really not worthwhile because we can't do anything with it. The only way we can deal with this file is we have to read it as a binary file. So guess what we're going to do next? We read it. Guess what we got to do now? We're going to read it. We're going to use the file input stream. Last time we used the file output stream, and we used the data input stream. So they're identical in the sense of how they're used. The file input stream basically opens the file, establishes a connection. Data input stream basically takes the file input stream, basically gets it ready to read and points us to the very first record. So in this case, we say file input stream, fstream equals is instantiated as a new file input stream, myinfo.dat. So that opens the file, establishes the connection. Then we got data input stream, input file, instantiated as a new data input stream with the fstream. So it basically gets the file ready to read and is pointing to the very first record. Now, something that they didn't cover in the previous one, but we could do this in one step. I could say data input stream, input file, is instantiated as a new data input stream. And inside of the parentheses, I'm going to instantiate it as a new file input stream and then the path to the data file. So it's kind of a nice little shortcut. I mean, it's going to save you one line of code, but it's still kind of nice. The file stream constructor will throw a file not found exception if the file named by the string argument cannot be found. Okay, so just realize that. It has a built-in exception. So here's some of the data input stream methods. I've got close. Again, once we open a file, we do have to close it. This will return a Boolean called read Boolean. Read byte will return a byte. Read char will return a char. Read double returns a double. Read float returns a float. Read int, read long, read short, read UTF. So kind of think of it this way. The write is kind of like it has nothing but setters. The read, on the other hand, has nothing but getters. So, because really, if you think about it, that's what the write does. There's a writing stuff to it, so we're doing sets. Where the read is basically gets, where all we're doing is getting the data. So let's open up the read binary file. And it's pretty much just like the other program, except this time, notice we've got a throws IO exception. We got except this time it's going to read. We got an int number, Boolean end of file equals false. We got file input stream, fstream is instantiated as a new file input stream. We got numbers.dat. So it's going to read that file we just created. Again, it's a binary file. It's going to read it now. The data input stream basically then gets it ready to read. The fstream is pointing to the first record. And we display reading numbers from the file. While not end of file, it's already set to false. So while not false, we're going to try. Notice we got a nice, we're using a try catch here. While we're going to say number is equal to input file.read int. We're then going to print that number plus a space. Notice it's not a print ln, we're doing a print, so it's going to print straight across. Catch EOF exception. So every time it does a read, it's going. If we read and the very next item is the end of file, it's going to throw this catch right here. And we've got end of file is now equal true, which then causes us to drop out of that loop. We're going to display done, and then we're going to close the file. So pretty simple. Let's run it and it says reading the numbers from the file, 2, 4, 6, 8, 10, 14, 12, 14. And then it says done. So we can write to a binary file, we can read from a binary file. Any questions on that? Not really too much difference between how we process it from the previous file that we've created before. Over on page 738, it talks about reading UTFs or reading strings, and that's where the UTF comes into play. When the data input streams class, the read UTF method reads from a file. It expects the first 2 bytes to contain the number of bytes in the string that the string occupies. So when it writes to a binary file, it's going to write to check bytes that basically tell how much data is in this particular UTF file. Then it reads that many bytes and returns it as a string. So that's kind of cool. What it says is, hey, the first 2 bytes say, hey, the length of this UTF is basically this long. And so what happens is it basically then says, okay, I'm going to read that much code past it to check bytes. For example, assuming the output file references data object stream, the following uses the code write UTF method to a string. So string name clo, output write UTF name. Assuming that input file references the data in the object, the following statement uses the read UTF method to read the UTF-8 encoded string from the file. String name input file read UTF. Remember that the read UTF method correctly reads a string when only the string is written. So what it does is this. Is the first 2 bytes. So this whole process says the first 2 bytes says, hey, this thing is 5 characters long. So what it does is it goes past those 2 bytes, it goes past, and then it reads 5 characters into this string name. One last thing of this section, if we need to append, so if I have an existing binary file, remember what it said before, it says that if you open it up, it will basically overwrite or erase whatever's there, unless we do this. If we say file open stream, fstream is instantiated as a new file open stream, we got myinfo.dat, comma true, that says, hey, if this file already exists, open it for append. So it's going to open it, and it's going to basically say, hey, when we do our data output stream output file, new data output stream fstream, it's going to basically put the pointer at the very end. So it's going to have us our read pointer sitting at the very end of the file. I'm sorry, yeah, pointer at the very end so that we can write. So that the very next time we write is going to be at the end of that file. So any questions on binary files? Okay. So the next one we're going to talk about is this thing called random access files. Now, random access files, so far, I don't know if you remember the old cassette days, we had cassette tapes. When you put a cassette tape in to listen to music, if I wanted to listen to song number, I don't know, 5, I'd have to fast forward past song 1, song 2, 3, and 4 to get to song number 5. Well, that's pretty much the files we've been using so far. We've been using those kind of, they're called sequential files. So you write a record, and then you write a record, and then you write a bigger record and a smaller record. Okay, so they're kind of varying in size. Well, later on in life, we got these things called CDs. And the CD, you put the disc in, and you could say, hey, take me to song number 5, or take me to song number 6, or take me to song number 7, and it would automatically go to that song. We didn't have to fast forward to get to it. Well, that's kind of what a random access file is. If I want to read file number 5, I can say read file number 5. But with random access files, each record has to be the same exact size. So if I basically created a random access file and I said I'm going to have these 2 fields in there, each field is going to be the same exact size. So let's say I've got name, first name, and last name. I've got 10 bytes and 10 bytes. So it's a total of 20 bytes. That means each name field is going to take up 20, 20, 20, 20. And that's where we can say, if I want to read name number 3, it knows to go 20 and then 20, and the third one starts right there. That's how it knows where they are. So that's kind of the secret for random access files, is every record is the same exact size. That way it knows where the starting position of each record where it resides. So it says right here, items in sequential files, access files are accessed one after the other. In the random access file, we can access them in any order. I can grab song number 5 and come back and read song number or file number 3, and then number 7 and number 2. We don't have to basically read them in sequential order. So to create a random access file, we go ahead and we use a random access file class. I'm going to create a random file object. I'm going to instantiate it as a random access file, and this is where I put in my data.dat. And now I'm going to either use an R or an RW. R is basically read only, and RW is read write. If you open a file in R mode and the file does not exist, a file not found exception will be thrown. If you open a file in R mode and try to write to it, an IO exception will be thrown. So if I try to open a file for read and then I try to write to it, it says IO exception. Sorry, you cannot write to a file that's been opened for read only. If you open an existing file in RW mode, it will not be deleted. The file's existing contents will be preserved, so it will do an append. If you open a file in RW mode and the file does not exist, it will be created. So the default for a random access file is append. It will automatically append. So let's take a look at write letters. Notice that I do have an import java.io. That's where the random access file comes from. So let's take a look at this. Notice I've got a throws IO exception attached to my static void main, because somewhere in here we could potentially have an exception. I'm going to create a char array. It's going to be called letters, and I'm going to load it with the entire alphabet, all in lowercase. I then write, opening the file. Random access file, rand file, is instantiated as a random access file, a new random access file, and I'm going to say letters.dat rw. And then I got system, println, writing the data to the file. So then what I'm going to do is I'm going to go through my for loop, one element at a time of this array up here, and I'm going to say random file dot write char letters I. So it's going to grab each element from letters. And notice I'm doing a write char. I don't know what else is here. If I type a WR, I've got write byte. write boolean, write byte, write char, write double, write float, write int, so on and so forth. Okay. So once that for loop is done, we say random file.close. We write done, and then the program ends. So kind of like the very first program we had for the binary write, nothing too exciting happens. When we click on the run button, it comes up and says opening the file, writing data to the file, and done. Now again, if I open this, I go to my workspace, I go to chapter 11, and I open up letters.dat. Notice that it's got this unprintable thing A, unprintable thing B, unprintable thing C, all the way to Z. Now, so after this program executes, the letters alphabet will be stored in the letters.dat file. We got a thing called the file pointer. The random access file class treats a file as a stream of bytes. The bytes are numbered, with the first byte being 0, the last byte's number being 1 less than the number of bytes in the file. These byte numbers are similar to an array's subscripts, and they're basically a way to identify the locations of the file. Internally, the random access file keeps a long integer value known as a file pointer. The file pointer holds the byte number of the location in the file. When the file is first opened, the file pointer is set to 0. This causes it to point to the first byte in the file. When the item is read from the file, it is read from the byte that is the file pointer is pointing to. Okay? So to use it, we use the seek method. And in there I have the long and position, which is basically the file pointer. So, random access file, new random access file might read, and then I can say file.seek, because remember file is the name of the object, file.seek 99. Byte B equals file.readByte. Okay, so we create a new byte object B, and it's going to be equal to the file.readByte, where that file pointer is currently sitting at. This code opens the MyInfo data for reading. The seek method is called to move the file pointer to byte 99, which is the 100th byte in the file. Then the readByte method is called to read byte number 99 from the file. So this will read byte 99. After the statement executes, the file pointer is advanced by 1 byte, so it moves to byte 100. So if we want to keep processing, we'd have the following code. File seek 49. The file pointer is now sitting at byte 49. Now, when I say int I read int, it's going to move the file pointer to byte number 49. Then the read int method is called. This reads an int from the file. Now remember, ints are 4 bytes long. So at position 49, it's going to read 4 bytes. And the pointer at that point is going to be sitting at position 53. 49, 50, 1, 2. Okay? Yeah. The file pointer advances 4 bytes, so it's sitting at byte 53. So down here, here's another example. We open up letters.dat, we read it. We say random file.seek5, it reads the character. We load we create a new char ch, and we go ahead and read that from the random access file, read char. It's going to read just 1 character. So read int reads 4, read char just reads 1, read long is going to be, I think, 8, and like read double is going to be like 16. So here's the layout of the letters.dat. If you remember, when I opened it, it has a null, well, it says null, but it's some character in A, some unprintable character in A, B, so on and so forth. So each record is 2 bytes. So that's what we see here. We've got a character is in position 0 and 1. The next character starts at 2. The next character starts at 4, then 6, then 8, then 12, 14, so on and so forth. So, the way we would set this, now here's how we have to set this up for our particular file. If they're set up as 2 characters, guess what we do? We create a final int called char size, and it's 2. And it says, I want to move the file pointer to character 5. I'm going to say randomFile.seek char size times 5. So char size is 2. I want to go to record number 5. So it's going to come all the way over here to 10, and it's going to read whatever character or whatever item is in 5. We're going to read that char, and we're going to basically say the 6th character is char. Now, because remember, if I move it to number 10, there's 1, 2, 3, 4, 5, so I think, yeah, so 0, 2, 4, 6, 8. So 1, 2, 3, 4, 5, which is number 8. So let's open up read random letters. Let's take a look at this guy. So I've got a final int char size equals 2. So each item is 2 bytes. But there's only 1 character in there, okay? We got long byte num. We got char ch. We go ahead and create our random access file object. So here's a random access file. Random file is instantiated as a new random access file. We're going to open letters.dat. We're going to do a read. Byte num is equal to char size times 5. Byte number is long. So char size times 5 is 10. We're going to say random file.seek byte num. So we're going to go to the 10th item. We're going to place our pointer right there. And then we're going to read that char at that position and put it into ch. And then we're going to print it. And then I want to read the character in the 10th position. So I say byte num equals char size times 10. Random file.seek byte num. Now it's going to basically go to the 20th position. It's going to be, so our pointer now is sitting right there at the 20th position. We read that char and put it into ch, and we print ch. Then I want to read the 3rd character, or 3rd record. So I say byte num is equal to char size times 3. So 3 times 2 is 6. It's going to be sitting at the 6th position. The pointer is going to be sitting right there at the 6th position. I read the char at that position, load it into ch, and then I print ch. I close the random file, and we're done. When we run this, look what it did. So the 5th item, so A, B, C, D, E, F, which is actually the 6th, because remember, we're starting at 0. So really it's 0, 1, 2, 3, 4, 5, which is actually number 6. And that happens to be F. And then 20th letter is K, and the third letter is D. So 0, 1, 2, 3, 0, 1, 2, 3, which is A, B, C, D. Does that make sense? So with random access files, really what we need to know is the file size here, or record size. I could actually call that record size, not char size. And again, each record is going to be the same exact size. That was called right binary. No, not right random access. It's called yeah, right letters. Yeah, so here's what's weird is we're writing just one character. We're writing one character in there, but it's taking up 2 bytes because it's got the pointer in there as well. Okay, now the last section of this chapter deals with this thing called object serialization. And so here's kind of the long and short of object serialization. We're writing Java code. Somebody could be writing Python code. Somebody could be writing C++ or C# or any one of these other languages that are out there. If we wanted to write to a file that any one of these other programming languages could read, we would probably want to use object serialization. When we serialize something, think of that. I don't know if you have ever dealt with WordPad and Windows, but WordPad wrote to what's called rich text format. And rich text format is readable by any word processor out there. So it's kind of the generic format for writing a document. So object serialization is kind of that same thing. It says when an object is serialized, it's converted into a series of bytes that contains the object's data. If the object is set up properly, even the other objects that might contain as fields are automatically serialized. The resulting set of bytes can be saved to a file for later retrieval. In order for an object to be serialized, its class must be implemented, or it must implement the serializable interface. The serializable interface, which is a Java.io package, has no methods or fields. It is only used to let the Java compiler know that the object of the class might be serialized. In addition, if the class contains objects of other classes as fields, those classes must also implement the serializable interface. So, how we use it is we do the import.java.io. I could do java.io asterisk and grab everything, but we can just use the dot serializable. Then in my class, when I create my class, I say implements serializable. I create my file output stream. There's a new file output stream, objects. And my objects, this is a file output stream. Now I've got object output stream is instantiated as a new object output stream, outstream. And to serialize an object and write it to a file, we use the object output stream. So we just used the file output stream previously, but we can use it with the object output stream, which basically serializes it. So I could create a bank account object, a bank account to object, and I'm going to, and my constructor, I'm going to set the balance to 5,000. Then I can say object output file dot write object account. This is going to write a complete object. The write object method throws an IO exception if an error occurs. The process of reading a serialized object's bytes and constructing it. Now again, so think about this. So serializable just puts it in a generic format that any one of these other languages, if they can read a serialized object, they can now read it in. So it kind of puts it in a format that anybody can use. So file output stream end stream is instantiated as a new file input stream objects.dat. And then here's my object input stream. Object input file is instantiated as a new object input stream using the end stream file that was just created up here. And same sort of thing. This opens the file, makes the connection. This sets it up for reading and basically is pointing at the very first record. And here's my bank account to account. So I just created a bank account to object. It's got nothing in it right now. There's no methods, no nothing. And then I say account is equal to bank account. Now here's what's kind of cool, is I'm making it equal to an object input file dot read object. But notice in parentheses I've got bank account to. Remember the cast? I'm saying cast this as a bank account to object. And so whatever I get from this read object, convert it to a bank account to. So I'm casting it as a bank account to object and then putting it into account. Again, this could be, instead of an object or a class, that could be an int, could be a double, it could be any one of the different primitive data types, or any object. Could be a string as well. The read object method returns the deserialized object, okay? So this up here, when I do a write object, that serializes it and puts it into this object. When I basically read a serialized object, I'm going to read it into another object. This deserializes it. So think of it kind of like a zip file. You know how we take a zip file, we take a whole bunch of stuff, and we're able to scrunch it down into a smaller, and then basically pass it off. And then when we unzip it, it just basically unpacks it, and then makes it usable. Well, this is kind of what serializable does. It basically compacts it down into this object that can be read by anybody. And then when we bring it into that program, I can then read it, which deserializes it and puts it into an object that's usable for me to basically utilize. Does that make sense? So let's look at these serialized objects. And notice that I've got a throws IO exception on my public static void main because there are some exceptions in here. And I've got a double balance. I've got a constant num items equal to 3. I'll create my scanner keyboard, and here's where I create. Notice I'm creating a bank account to array. The name of the array is accounts. It's instantiated as a new bank account, and then we're going to create 3 items because num item has 3. So when we get done with line 23 and 24, we now have a 3-element array of bank account to objects. Then I'm going to create a for loop to go through the accounts one at a time. I got system.out_print, enter the balance for account. Now, remember we got I plus 1. I don't want to say account 0. I want it to say 1, 2, and 3 instead of 0, 1, and 2. And then I get the balance from the keyboard next double. And then I say accounts I is instantiated as a bank account to balance. So this up here creates 3 empty shells of bank account 2's objects. Right here on line 35 is where we actually instantiate it and put the guts inside of that empty shell object. And there I got balance. Now, this is where I create a output stream. Outstream is new output stream objects.dat. That opens the file and makes the connection. Objects output stream, object output stream. This now basically is getting this file for reading. For writing as a serialized object. Now I'm going to step through the accounts.length. So I'm going to go through this 3 times a time, and I'm going to say object output file.write object, and it's going to write that bank account to object as a serialized record in this object output file. I then close the file, and it says the serialized objects were written to the objects.dat file. So line 47 serializes that object and then basically puts it into the file. Now, again, when we run this, okay, I'm going to go ahead and type in 5,000. Account 2 is going to have 2,500. And account 3 is going to have 1,800. And it says the serialized objects were written to the objects.dat file. Now, if I come out here and open up objects.dat, well, guess what? We're going to see some code in here. We're going to say unprintable, bunch of chap 11.bank account 2. We got balance. The rest of it's all unprintable because, again, it's in a serialized object format. And what's great about this file is I could take it into a Python file or Python program, deserialize it, and basically utilize that data. Any questions on that? I'll take that as a no. Okay, if we go out here to Eclipse, and now we're going to open up the deserialized objects. So, got double balance, we've got a constant num items 3. I create my file input stream, nstream, and it's going to basically instantiate as a new file input stream, and it's going to basically place the file name objects.dat. So opens that file, makes the connection. Object input stream, object file, instantiates an object input stream, and it's going to bring in that file input stream, nstream. It basically gets it ready to read with the pointer sitting at the very first record. We create an array of bank account 2 again. How many? The num items, which is 3. We're now going to step through that array one element at a time. So again, remember, this guy just created 3 objects, bank account 2 objects of empty shells. There's nothing in them. As I step through this, I'm going to say accounts I is equal to, and this is where we instantiate each of those records. It's going to read the object via the object input file, deserialize it. This casts it or converts it to a bank account 2, and it puts it into that element in the array. Before I continue, if I do a period right after this object input file, notice that if I come down, I can see read, read with byte, read all, read boolean, read byte, read char, read double, read fields, read fully, read int, read line, read long. So you can see there's a whole lot of different reads in there. Read object, which is what we're doing because we're actually reading a bank account to object. So once we read each one of these items, deserialize it, and throw it into the array, next thing we're going to do is close that file. And then we're going to come in here, and we're not, since it's deserialized, now we can actually go into each item and get the balance. So we're going to go through the accounts one at a time. I'm going to say account I plus 1, because we want to do 1, 2, 3 instead of 0, 1, 2. $, account I get balance. So we're going to get the balance of each one of those accounts after it's been deserialized. We run it. And look at that, account 1, 5,000, account 2, 2,500, account 3, 1,800. Any questions? The very last thing this chapter talks about is this thing called serializing aggregate objects. So if you remember aggregate objects, if I have an object as an instance variable and so I have another one, if a class implements a serializable interface, then all of the fields in that class must be serializable. This isn't a problem for primitive variables because they're already serializable just as they are. So primitive data types are really already serialized. However, if the class has a reference variable as a field, then the object's reference to that variable should be also serializable. This means that an object class should also be implemented. So if we have an aggregate, remember how we had the student, we had the course, and it had the teacher object and the textbook object? Well, each one of those objects they have to be serialized as well. So we would have to have that, it would have to basically, where is it? It would have to have that, where it calls that, I think that's the binary one. Yeah, that's the binary one. Anyways, no, it's this one. Which one was it? We have to implement. Yeah. Oh, that's what it was. It's the bank account. That's right. If I look at bank account 2, it has to implement serializable. So if I take this off right here, so I take that off, and I go back to serialize object. If I try to run this now, notice I get basically an error. It's going, hey, in order to basically serialize this, we have to implement the serializable interface for that object. Which object? The bank account 2 object. So the bank account 2 object must have implement serializable as the class in order to basically serialize this entire object. So that's basically what they're saying in that chapter right there is, like, for example, the course where I had teacher and textbook, the teacher and the textbook would also have to be they have to use the implement serializable. If it doesn't, then we can use what's called the transit keyword that would be used as a reference variable declaration, private transient, some class, and then basically whatever the reference variable is. Because of the transit keyword, the compiler will skip the object's reference by by the ref var, by the reference variable during the serialization process. Unfortunately, the string class and most of the other classes found in Java API implement the serializable interface. So, string already basically does it. We don't have to serialize a string because it already implements the serializable object or interface. Any questions on that?